Yes. Okay, so today I'll talk about single file processes. So the title is little changed what I had initially announced. Initially it was fluctuations and correlations, but I also added distributions. So I'll talk about distributions also. So the single file, the study of single file processes is an old problem, and recently it has received renewed interest because of developed experimental techniques and new experiments, and people have started asking new questions. And so I'll present our some new results in single file processes in two different single file models. So this work is done in collaboration with Julia Sividini. He's a postdoc in Weizmann Institute of Science, Israel, and David Mukamel. He's a professor in Weizmann Institute of Science, and Sattu Mujumdar is a professor in University of Paris, Orsay. So these are the references of this talk. Okay, so motion of particles in crowded medium is a frequent problem in physics, chemistry, biology. Imagine such a situation that you have a particle which is moving inside gas of other smaller particles, which are much smaller, and you want to describe the motion of this big particle. And often this is done by writing down such a Langevin equation phenomenologically. And this phenomenological description is possible, you can do that only when the time scale of the motion of smaller particles is much smaller than the time scale of the motion of the big particle. But what happens if the sizes or the time scales of these particles are comparable, as you see every day in in Bangalore? Uh, in this case, such phenomenological description does not provide accurate description, and one needs to consider the full interacting many particle problem. And usually what happens that at very small distances, the interaction is strongly repulsive, and it may be weakly attractive at large distances. Such situation appears in various situations, various contexts. For example, in active microrheology, where one pulls a big particle inside a colloidal solution, then one manipulates fluids drops inside a microfluidic devices. Then traffic flows, also interacting motor proteins along actin filaments, ion transport through membrane pores, and there are many other situations where this situation appears. And one of the common feature in all these situations is the following, that since there are strong repulsive interactions at short distances, any displacement of one particle creates a density perturbation around that particle, which in turn affects the motion of those particles. As a result, the motion of various particles becomes strongly correlated. And that effect of this correlation is dramatic in one-dimensional system, where particles are confined to move in one dimension. And since they are interacting via strong repulsive forces at short distances, it is very rare that each particle will overtake the other particles. So mainly they will kind of maintain their initial order, they will not overtake each other. And motion of one particle will be hemmed by the presence of all other particles. As a result, if you look at the motion of one particle, one tag particle, which is similar to any other particle, it's not a different particle, mostly it has the same dynamics, it just carries a mark. If you look at the motion of this, then the motion of this particle, it will be completely different from its motion when it is free, it's moving in a free space. For example, if you look at a free Brownian particle, its mean square displacement grows linearly with time, as diffusion. But if you put the same Brownian particle in presence of other impenetrable particles in one dimension, then the mean square displacement of the same particle grows subdiffusively, square root t. So it seems it has the presence of other particles in one dimension with strong repulsive interactions, has dramatic effects. It's kind of interesting to study this kind of system. And one of the important quantity that people are interested in is the displacement of the tag particle. And people have, the study of this quantity have started long back, actually, by Jepson and Harris. They studied this quantity, and they showed that if the individual particles are performing ballistic motions, then the mean square displacement of a tag particle grows linearly with t instead of t square, whereas for Brownian particle, as I mentioned, it grows as square root t instead of t. And these results are for hard point particles. So this quantity is very interesting, and since then there are a lot of studies, and lot of people have studied this problem in different model systems and in different using different mechanisms and asked different questions also. Very recently, people have got interested in finding the distribution of this quantity of this stack particle displacement, and recently Abhishek, Sanjeev, they computed the large deviation function using a microscopic technique, and also people Krapivsky, Tridev and Kiron, they computed the large deviation function using a hydrodynamic approach, but for specific initial configurations. So in this case, in this talk, I'll talk about this problem computing the distribution, but for some arbitrary initial configurations, which I'll talk later in detail. Not only that, people have also looked at inhomogeneous single file systems in which the tag particle is driven locally. And as a result, because of this drive on this tag particle, there will be inhomogeneous density profile created. And one is interested in the inhomogeneous density profile also, and also the fluctuations around this inhomogeneous density profile, density fluctuations, and also the force velocity relations and mean displacement. There are various other questions people have started asking recently. So in this talk, I'll talk about two problems. One is homogeneous single file motion, where all the particles have the same dynamics, and we just mark one particle and observe the motion of this particle. And for this case, I'll present some exact results on the full probability distribution of the displacement of this particle for arbitrary initial configuration of all the particles. And in the second part, I'll consider different single file motion where one particle is driven, and in this case, I'll present some hydrodynamic approach to compute the fluctuations and correlations of displacements of not only the tag particle but also of other particles and the correlations for between any two particles. Okay, so let's start with this part. So we consider 2n plus 1 particles initially on a line, and let's assume that the tag particle is at origin at x equal to 0, and there are n particles on the left of this particle and n particles on the right of it, and their initial positions are represented by these x variables. And in time they evolve and they reach, say, at time t in this configuration, which are represented by these y variables, and their evolution is described by some propagator, multiparticle propagator, which I'll describe later in the next slide. And for this problem, we are interested in the distribution of the displacement, which is y naught minus x naught. X naught is 0, so we are interested in the distribution of y naught variable. And the propagator, in this case, I'm assuming that the particles are hardcore point particles, so that means they're hardcore repulsive. And I'm also considering that each of these particles, when they are free, they are described by a single particle propagator which has this scaling form, where sigma t is some time-dependent length scale and g is some scaling function. For example, if you consider Brownian particles, then g is the Gaussian, Gaussian function. So if you consider ballistic particles, but their initial velocities are chosen from Maxwell distribution, then also this function is Gaussian. But you can choose any other particles also. And this is the form I'm choosing for the single particle propagator. And since the particles are hard point particles, so the propagator will be in this form, that the product of the propagators of the individual particles, and then you have a sum over permutations of all the possible permutations of the initial positions over the particles. So this is the multiparticle propagator, which describes the evolution of these 2n plus 1 particles to this configuration. This is the probability that these particles go from this configuration to this configuration in time t. So once we have this propagator, then what do we want? We want to find out the distribution of this. So for doing this, we have to integrate all the final positions on the left of the middle particle and all the final positions on the right of the middle particle. And these integrations are not kind of independent, they are ordered integrations. because they cannot overtake each other. So you have to perform these integrations in a ordered fashion. And once we have done this, then we'll do the rest of the two tasks, average over initial configurations and then take the thermodynamic limit. So initially, we assume that the particles are starting over a length scale L, n particles, and then take n going to infinity limit and L going to infinity limit, keeping n by L, which is rho, fixed. That's how one can take the thermodynamic limit. Okay, so let's perform this integration. One can actually perform this integration using the permutation symmetry properties of this propagator. But instead of going there, let us do this integration in a physical way. And to do that, we observe that there is a mapping of interacting workers to a corresponding non-interacting workers problem. So we consider two problems. So corresponding to this interacting worker problems where the workers cannot overtake each other, cannot cross each other, they just reflect off each other. And corresponding to this initial configuration, we consider the same initial configuration, and now we make the workers to be non-interacting, they can cross each other. So this is the two problem, and the mapping is that the probability of the displacement of the zeroth particle in this picture, in this problem, in time t is same as the probability of the difference between the positions of the zeroth particle at time t and the position of the zeroth particle at time t equal to 0. Obviously, you can see that the particle which was the zeroth particle at time t equal to 0 may not remain the zeroth particle at time t equal to in the final time. Some other particle can come and become the middle particle because there's non-interacting, they just cross each other. So this is the mapping, and it is easy to understand this mapping because for each such history of configurations, the trajectories of particles, if the initial configurations are same, then one can get a valid history here by interchanging the labels whenever any two workers cross in this picture. And since the particles are hardpoint particles, then the probability of these configurations is exactly same as the probability of these configurations because they are hardpoint particles. So by using this mapping, one can compute this probability that the middle particle, the tracer particle, has a displacement y0 in time t, given that the initial positions of all the particles are represented by this x vector, which is this. Okay, so let's compute this quantity. So I'll try to compute this quantity by the following physical arguments. So since this side is computed from the non-interacting workers picture using this mapping. So since the workers are non-interacting, any particle from the 2n plus 1 particle can reach become the middle particle and reach y0. Say mth particle, and what is the probability that the mth particle reaches y0 in time t? This is the propagator. Now since this particle is the middle particle at time t, then there has to be n particles on this side on the left of it, and there has to be n particles on the right of it at time t. Now what is the probability that a particle starting from x reaches at the left of y0 at time t, which is given by this g minus function, which can be obtained from a propagator by integrating the final position from minus infinity to y0. This is the probability that a particle starting from x reaches to the left of y0 in time t. Similarly, you can get the probability that a particle starting from x reaches on the right of y0 in time t, which is g plus. So now given these two probabilities, and these particles are non-interacting, so then the probability that there are n particles on this side and n particles on this side, you can write some products of these probabilities. But you have to make sure that there are exactly n particles on this side and exactly n particles on this side. So to do that, we introduce a variable epsilon, and it can take +1 and -1 for each xk. Xk is the kth particle which starts from xk position. If epsilon is -1, then the particle starting from kth position xk, kth particle, it reaches to the left of y0. Similarly, if it is +1, it reaches to the right of y0. And since any n of the rest of the 2n particles can reach there, then one has to sum over all possible configurations, respecting the condition that this is the middle particle. So how do we do that? We can do this by introducing this delta function, because exactly n particles have -1 values of epsilon, and exactly n particles have +1 values for epsilon. If you add, it has to be equal to 0. So by introducing this condition, you can take make sure that this particle is the middle particle. Okay, so now this mth particle can be any one of the 2n plus 1 particles. We have to sum over all the particles. So this is how you can compute this distribution, and one can simplify by introducing some integral representation of the delta function, and perform some manipulations and calculations. One can show that this quantity can be elegantly expressed by this simple formula, which is a ddy naught of some function for where we have a factor for each of the particle starting from xk, and k goes from -n to n. And one can easily check that this distribution is normalized and is exact for any given initial configuration for n particles. Okay, so we have performed the first task. Now we have to do the second, perform this task, second task and third task. We have to average over initial configurations. So usually people consider this initial configuration that the particles are initially arranged at regular spaces, which means that the initial position of the particle is proportional to their labels, and the proportionality constant is the gap, which is basically the inverse of the density. And that's such a configuration in the thermodynamic limit will give you uniform density. So people usually consider this initial configuration. So we can actually incorporate this initial configuration and compute all the results that have been that are existing in the literature and in matches. But we can also incorporate other general initial configurations. For example, we can consider uniform density, but the density at the left of the particle is different from the right, different from the density on the right of it. And one can compute this explicitly, and it looks like this, which involves some Bessel functions, and these are some functions involving the propagator. But this looks a complicated expression, but if you compare that with the simulation, it matches very nicely. And because of this density difference, the tag particle feels a velocity, it acquires a velocity, and it moves linearly with time, and the velocity is proportional to the difference between the densities. Not only that, one can also consider more general initial configuration. For example, inhomogeneous density profile, more inhomogeneous throughout the system. In this case, if you can as an example, you can consider that the particles are depending on their labels, they depend on their labels non-linearly, where alpha is some number, positive number, k is the label, and the position of the particle, the kth particle is proportional to mod k to the power alpha. And for any alpha, one can compute this distribution. That expression is quite complicated, that's why I'm not showing it, but it matches quite well with the simulation. Not only that, here I'll present some present its large deviation function, and one can show that this quantity has this kind of large deviation structure, or this large deviation function can be computed explicitly, which depends explicitly on lambda, which is reflected on the moments, definitely, and you can show that the mean square displacement of the tag particle when the particles are starting from this initial configuration is proportional to sigma t to the power 2 minus 1 over alpha. And the interesting, whereas for uniform density, it's proportional to sigma t. The interesting fact is that you can see that even in the large time limit, the moments, even the full distribution depends on how initially the particles are arranged. And if they are arranged, the information about the initial configuration comes through this feature in this. And also, one can compute the full joint distribution. For example, if you consider the Brownian particle, then in this case, which is a parabolic initial configuration for alpha equal to 2, this quantity should grow as 3 over 4, which we also see in the simulation. So this is a summary of the first part, that we can compute the exact distribution of the tag particle for arbitrary initial configurations, and we see that the statistical properties of the tag particle motion depends on how initially the particles are arranged. And this method can be easily extended to multi-tag case. For example, if you have 2 tag particles or 3 tag particles, it will be similar to the expression will be exactly same, except that there will be more derivatives. Initially it was ddy0, now it will be ddy1, ddy2, like that. Easily extend this method. Okay, so now let me go to the second part, where I will consider inhomogeneous single file motion, where this stack particle is driven locally. And in this case, I'll consider a different model for the single file motion. The model is the following, that the particles perform a random average process. The process is the following: the particles are moving in one dimension, and they move by the following rule. So you choose one particle at random, say the ith particle, and then it jumps to the right or to the left with equal rate half. But if it decides to jump to the right, then it jumps by a random fraction of the space available till the next particle in that direction. And the random fraction, random number, is chosen from some jump distribution R eta. So for example, the evolution rules can be expressed in this explicit equations, that the ith particle, if it jumps to the right, then it does that with this probability. Similarly, if it jumps to the left, then it does that with this probability, and if it doesn't, with this probability. Note that this single file motion is different from the previous single file motion, because there is no single particle dynamics in this. You cannot imagine a single particle performing this motion on an infinite line. There is no single particle dynamics. However, all the particles cannot overtake each other. So in that sense, it's also a single file problem. So this process was introduced by Ferrari and Fontes in 1998. And then since then, this model has found many applications in various contexts. For example, in traffic model, wealth distribution model, interface side models, etc. Okay, so but we are interested in the situation where we have a tracer particle which is driven, and how do we drive that particle? So all other particles are jumping to the right and to the left with equal rate, but for this case we make the rates different. It jumps to the right with rate p and to the left with rate q, and p is not equal to q. And here throughout the talk, I'll assume p is greater than q, so that the particle actually predominantly moves in this direction, in the right direction. And for this situation, I'm interested in the following dynamical properties: the mean displacement of all the particles from their initial positions, and also the variance of the displacement. And not only that, also I'm interested in the correlation between the displacement of any two particles. And to compute that, it seems convenient that one maps this process to an effective mass transfer process. And the mapping is the following: that corresponding to the motion of these particles in this RAP, random average process, there exists a mass transfer process on a lattice. And the mapping is the following: that the kth particle in the in RAP process gets mapped to a link between k-1 and kth site in the mass transfer picture. As a result, this particular this special particle gets mapped to a special link between -1 and 0, because the rates of mass transfer will be different, whereas rates of mass transfer here are half. And the mass at one site is exactly same as the, say at kth site, is exactly same as the gap between the kth particle and the k-1th particle. That is the mass. And this is the mapping. And once you have done this mapping, then one can write down the dynamics of the masses also. So this dynamics, these rules can be translated into these variables. For example, if this particle jumps here, then a mass or the space, this space, random fraction of this space, which is equivalent to the random fraction of this mass, gets transferred to this side with rate half. Similarly, if it does that, then some fraction of mass gets transferred to this side. So equivalently, you can write down the full dynamics, and where eta is the random variable chosen from the jump distribution R eta. Okay, so given these dynamics, we want to find out the following, these quantities. But since we are interested in the large length and time scales, it seems convenient that we consider a continuum description of this process. And in this case, we can represent the mass transfer process in terms of the evolution of a mass density profile, which is in the continuum limit. And since the mass transfer process is in this process, no mass is getting destroyed, only gets transferred from one side to another side. So this evolution has to be in the form of a continuity equation. So there is a current, and this evolution is in the continuity form. However, the mass transfer process is stochastic, so this current should have some fluctuations. So it turns out that the current has a regular diffusive part, which is this is the diffusivity and this is the gradient of the local mass density, and it has a fluctuating part which has the usual mobility, and this noise is a white Gaussian noise with mean zero and delta correlation. And this mobility, one can show that it depends on the local density as local density square, where mu and mu2 are the moments of the jump distribution. So these equations are not ad hoc actually. You can actually phenomenologically argue to get these equations, but one can also rigorously derive these equations starting from these microscopic rules and using the Markov property of the dynamics and using the large deviation techniques. One can actually prove these equations, the correct continuum limit. So once we have that, then we have to find out the displacement of the kth particle in terms of this density profile. And the relation is the following. So one can it is easy to understand. So consider this term. So this is the position of the kth particle with respect to some reference point at minus infinity. It's just basically you add up all the gaps and it becomes the position of the kth particle with respect to some reference point at minus infinity at time t. Similarly, this is the position of the same particle with respect to the same reference point at minus infinity at time t equal to 0. So individually both the terms are infinity, but if you take the difference, that is a displacement which is a finite quantity. And you can see that this displacement is basically amount of mass transferred across the point k in the mass transfer model. Exactly that. And also observe that this quantity is a linear functional of this density field. So the problem boils down to the following, that you have two fields, mass density field and the current density field, which has this evolution, stochastic evolution, and we have a functional of the field, linear functional of the field. So given the stochastic evolution of the fields, we want to find out the statistical properties of this linear function. This is the problem, it boils down to this. And how do we do that? To find out the statistical properties of any quantity, you start with a generating function. Since we are interested in 2-point functions, so we consider this generating function where we introduce two auxiliary characteristic variables, lambda k and lambda l, and we consider this characteristic function, and this average is done over the joint probabilities of the density and mass profiles and also their evolution. So it's sum over the space and also over the time, the integrations. And these profiles also have to satisfy the continuity equation at all times. So this is in some sense a delta function in the field variable in field space, x, z and t both. And once we have this quantity, then taking the derivative of the log of this quantity with respect to lambdas and finally taking lambda k going to 0, lambda l going to 0, we'll get the 2-point correlation function. So this is the procedure I'm going to follow. So what we have to do, we have to perform this integral. This is an integral, of course, because one has to do this average with respect to the joint distribution of the profiles. And this is a functional integral. This is a probabilities in terms of functionals, and these are the functional integrals. And this is the integration over the initial configurations, and this is the probability of the initial configuration. So how do we do these functional integrations? So usually what we do, we basically try to write down in the form of an action integral and do saddle point calculation. Here also we do that, and that one can go from this to this using Martin-Segiya-Rose formalism and write down a effective action and then perform a saddle point integration. So basically in the saddle point integration, what you do, you basically replace this integral by this quantity to the power minus s, where s is evaluated at the optimal profiles which are obtained by extremizing this action. These are basically Euler-Lagrange equations. And remember that sigma omega, which is the mobility, is proportional to omega square, the local density. So these are two coupled nonlinear differential equation one has to solve. And if you find out these solutions and then put it here, and then you get this quantity and take derivatives with respect to lambdas, you get the various moments. And by this procedure, one can find that the boundary conditions which have discontinuities because this particle is driven. So there are discontinuities. So this is the discontinuity in the density, and this is the continuity of the currents, and this comes from the auxiliary variables. And also it has some initial and final conditions also. So with these conditions, one has to solve this quantity, and you see that the lambdas appear in the initial and final configurations conditions. Okay, so we solve this and then put it back and find out this quantity and compute. And by doing this procedure, we find that mean displacement, variance, and correlations, all of them scale as square root t. Remember, mu1 is the first moment of the jump distribution. And that square root 2 behavior is modulated by some scaling functions of the scaling variable. Here the scaling variable is I by root t, here also it's I by root 10, it's a scaling variable of function of two scaling variables, I by root 10 j over root t. So this is what you observe, and then by this following procedure you can also compute these scaling functions. So I'm not going into the details of this computation of the scaling functions, but let me first focus on this, and then I'll discuss a little bit about this and mention some results about the correlations. So let us look at the mean displacement of the driven particle, the zeroth particle. So since this is driven, what do we expect? The displacement, will it grow as t or t to the power something? So to do that, so let us first, if we want to do a simulation, we cannot do a simulation on an infinite line. Right? So we do a simulation on a finite space, say on a ring. So assume that motion, random average process motion on a ring where we have a driven particle. And in this case, if you do a calculation, one can find that this quantity, the displacement of the zeroth particle in the large t limit has this behavior. It has a linear term and then has a square root t term, and it's proportional to the drive, which is p minus q over p plus q. If p is equal to q, there will be no net displacement, but so it has to be proportional to the drive. And you see that these two terms suggest these are two competing terms. It suggests that there is a time scale of order n square. So below which this term dominates, and above which this term dominates, which means that at very small time, these particles know that there are other particles to kind of confine their motion, but they don't know that they are moving on a ring. On the other hand, when at large times, all the particles know that there are other particles and all of them are moving on a ring, and they acquire a velocity, and that velocity is inversely proportional to the density. So if there are more number of particles, their velocity will be smaller and smaller. So it seems that there is a crossover, and the crossover time scale is of order n square. So is it possible to describe this behavior in terms of a crossover function, which is a function of the scaling variable t over n square? And if it is possible, then this crossover function should have this behavior, this asymptotic behavior, in order to reproduce this behavior. And indeed, one can compute this crossover function, and it is given by this explicit expression, which has the right asymptotic behavior corresponding to the right expected behavior. And we compare the crossover function with the simulation, and we see very nice agreement. So this was for the displacement of the zeroth particle. Now if you look at the displacement of all the particles, like a displacement profile at time t, and as I said, all displacements grow as square root t, but it has to be modulated by a function, because if you look at a particle which is very, very far from the driven particle, that particle doesn't know really that there is a driven particle. It's so it has to be modulated by this, and that modulation has to decay. So this function, one can show that it is explicitly given by this, which has to be proportional to this drive, and it decays as e to the power minus x square on both sides. And this displacement is maximum at the zeroth at the driven particle. Okay, so this was the displacement. Now let us look at the variance. Once again, we start from the variance of the driven particle, the zeroth particle, and if this particle was not driven, the problem with the non-driven case was studied earlier by many people, and they showed that the tag particle variance of the position of the tag particle grows as square root t in the last t limit. But people are interested in the prefactor of this behavior. So this prefactor should now depend on the drive, which is quantified by this expression. So as I said, the b equal to 0 case, when this drive is not there, when p is equal to q, this case was studied by many authors like Rajesh and Shatto, and then Eli Barkai and Silve. And they found this interesting feature that this p-factor depends on how the system have been prepared initially. So they looked at two types of uniform initial configuration. One is quenched uniform initial configuration, which I had already discussed. I have already discussed this. The particles start from fixed initial positions and they are placed at equal distances. And that gap is basically proportional to the inverse of the density. And the other one is the annealed, in which case the initial configurations are chosen from some distributions. So initial configurations are random. However, if you take average over many initial configurations, then the average position is kind of uniform. It becomes exactly as this on an average. And then the average position is proportional to the labels, and the proportionality constant is also the gap, average gap between the particles. This is also, you can consider that as a annealed uniform initial configuration. And in these two cases, they found that this p-factor is different. You see that there is a factor of square root 2 different between these two. So we wanted to see what is the difference when b is not equal to 0. Can we find out this p-factor? And indeed, we can find out this p-factor using this hydrodynamic technique for any b. And we compare that in the simulation on which we see good agreement. So this was the variance of the driven particle. Once again, we computed the variance of other particles, of all the particles, say k, which is not only 0. And we find that this quantity also has the scaling behavior. So to do that, to compare with the simulation, what we do, we compute this quantity and then plot this quantity divided by square root t as a function of this scaling variable for different t. And we see that the data for different t actually collapse on top of each other, and that scaling, the collapse function matches with the theoretical curve. And here you see that the variance, this variance, so this is the driven particle, the zeroth particle. So the variance in front of this driven particle is very small because this particle is moving this way. So there is a very large crowd of particles. So the particles do not have much space to fluctuate. So that's why this it is very small. And then as you go further and further, the density becomes less and less, and ultimately reaches to the point where as if there are no driven particle. But here you see an interesting feature that by this argument you would expect that immediately at the back of this particle, the driven particle, there should be an fluctuation should be maximum. But you see that the maximum occurs at a distance of order root t. This is a scaling variable. So at order root t, this fluctuations occurs. We do not understand this feature very well, but this is quite similar to what happens in the exclusion process, as if that because of this driven motion, there is a vacancy perturbation created at the back, and which propagates as square root t. And that's why this the vacancy is largest, vacancy density is largest, you can say, at a distance order root t, where the fluctuation is maximum. And again, if you are very far, then you will reach to the same point, same value, as if there are no driven particle. So this was the variance. You can also look at the correlations, and once again we verify that the correlations which we compute in the simulation and plot that numerical value divided by square root as a function of the scaling variable. We have to, it's a function of two variables, we keep one of them fixed, and we see that data for different times match, fall on top of each other, and that matches also in with the theoretical result. So there are many other interesting features, but one of the interesting feature is that of course at large distances, this correlation should match with the situation where there is no driven particle, and it need match. And if you consider the correlation around this, which I am not showing the plot, the correlation sometimes has a flat region, which is also because of the crowding effect in front of the driven particle. Okay, so this is a summary of the second part, that we have computed different quantities, mean, displacement, variance, and correlations. And we show using an aerodynamic description and approach that these quantities grow as square root t, modulated by some scaling functions of appropriate scaling variables. and we expect that this, there are many microscopic single file motions for which the hydrodynamics is more or less the same, and because of that, these correlations will serve kind of benchmark to compare various the correlations in various other models. And also it is interesting to kind of extend this method for other single file models and to compute the large deviation functions. One of the main difficulty of computing the large deviation function is to solve those nonlinear differential equations, which was possible for Brownian particles because there you could do a Kohlhoff transformation, and by doing that you can make these nonlinear differential equations to linear equations and could do this. But for other cases it turns out to be difficult, but it would be interesting to solve and find the large deviation function.
So to my knowledge, Professor Ajeshu has studied the single file transport through nanotubes, if I'm not mistaken. So is it possible to compare some of these things with the experimental results that he has?
Yes, at least the large deviation functions, the initial part, the first part, the large deviation function or the probabilities actually those probabilities are quite exact. So even if you have 5 particles, then also you can compute the distribution of one particle and then compare. It's possible. People have computed no? The Bechinger's experiments. Yeah, but interesting would be in the second part where you have a driven particle. Now I don't know how to create such a driven particle in experiment. One driven particle in experiment, that I am not very sure.
A particle in a channel, one-dimensional channel, and look at the motion, but now you can put many particles in that, and we find some very funny coming together of these active particles and so on.
So one active particle, but all others are passive particles.
No, we have put one active particle and more than one active particle, then what happens? We can also put active particle along with the non-active particles in the channels.
Yeah, then one can compute the correlations and try to
so
compare
I think
this.
There are very simple experiments which can be.
So I had one question. So for this random process, I mean, if you had drive at all points, like P not equal to Q, then I guess you can't write a fluctuating hydrodynamic equation. That is.
If the drive is very small, then you can do.
You can still write, is it?
Yeah, if P minus Q is of the order of, say, if you are considering on a ring, then P minus Q is of order 1 over L, then you can still write.
Okay.
It's still a diffusive hydrodynamics with a drive. But if it is of order 1, then you cannot. But apparently it turns out that I remember that Bernardin 2 years back had given a talk on strongly driven systems where you can actually do the calculation and then take the limit, the strong limit. Probably that kind of calculations can be done. I'm not very sure.
Okay, so no, if there are no other questions, let's thank Anupam.